Okay, so 16. 16 on page 272. It says, people sometimes go for a walk after a big, this is a good one for Thanksgiving. Let's go walk off that big meal. I remember physics in college years ago. We were talking about calories and a problem, an idea just like this right here in a physics class. And the professor said, we were talking about forces and things like that. So we were making it much more technical than this problem. It was the same idea, forces and calories, motion and walking and everything. And Kurt Larson was the professor. And he said, for people who go out on a walk like this, that is not the type of force they need to exert if they're thinking about losing weight. The force that will allow you to lose weight is the force where you push yourself away from the table and don't eat anymore. And that's what this problem shows us. It says sometimes they go for a walk after a big meal to burn off calories. But it says to lose 1 pound, a person must burn 3,500 calories. So 1 pound of body tissue is 3,500 calories of energy for your body. So it says, suppose a person burns about 300 calories an hour by walking, which is about right. A brisk walk, 300 calories an hour. If they walk for 2.5 hours, how many pounds will the person lose? Well, we've got to figure out how many calories they lose and then change the calories to pounds. Oh, let me turn this off. So if 1 pound of body tissue is 3,500 calories, and we write it with a capital C because that's different than a little, then we could write conversion factors. We could use this one, or we could use this one, depending upon where we needed the pounds and the calories, top and the bottom, numerator, denominator. So if they walk for 2.5 hours, and in 1 hour they burn 300 calories, we could also do this. 1 hour is the same as 300 calories, or 300 calories is the same as 1 hour. So if we change this to 2.5 calories, what's going to, or sorry, 2.5 hours, what would that do to this number if we keep them proportional? Well, in 1 hour you burn 300 calories. How many do you burn in 2 hours? 600. So in 2.5 hours you're going to burn 2.5 times as many calories. So all we have to do with something like this here, just to show our work with the problem, is to write 300 calories over 1 hour multiplied by 2.5 hours. And then your hours will cancel out, and you're going to take 2.5 times 300, and that's going to be 750 calories. So you burn 750 calories walking for an hour. Or 2.5 hours, yeah, thank you, 2.5 hours. So question, did you guys do Thanksgiving? Did you eat a lot? You didn't eat a lot. You didn't eat a lot. Did you eat a lot? What's a lot? How much? Like 1 plate of food? 2 plates of food? 3?
2 plates of food and dessert.
And a dessert. So how many calories do you think was in what you ate?
Not a healthy amount.
Well, it depends on if you're a brown bear or not. I'll bet even if you didn't eat much, I bet you ate 2,000 calories. You don't think so? Really? I bet you ate more than 2,000 calories, even though you didn't eat a lot. If you ate 2 plates of food and a dessert, you're probably in the 10,000 calorie range, is my guess. Pretty close to it, especially Thanksgiving, because you got things like stuffing, which is like loaded with carbohydrates. And then you have desserts, which are like loaded with sugar. And if you eat any kind of vegetables that were things like, like squash or yams or Brussels sprouts that have bacon on them or stuff like that. And then it's just, the calories go up, up, up. The bottom line is this, you could walk all day, and you're probably not gonna be able to walk off a big heavy meal. Just because you don't use that many calories doing things like that. So that's part A. So that if they walk for 2.5 hours, how many ounces will the person lose? Oh, wait, we need to change this into pounds, don't we? So this is the number of calories that they lose walking 2.5 hours. So which of these two do we use to change it into pounds? The left or the right? Maybe think of it this way. You're gonna multiply by one of those fractions, and at the end, you're gonna wanna have pounds as an answer. One on the left, because if you write a pound here, and you do 3,500 calories there, the calories, top and bottom, cancel. So now we have 750 divided by 3,500. So, maybe it'll work. Right? Okay, yeah. So if you do 750 divided by 3,500, what does that come out to? Don't make me do the work. But I will. It's an ugly decimal number, isn't it? What's it rounded off to the nearest hundredth? 0.21. So it's about, so you're talking like 1/5 of a pound? So that's like 2 in the tenths. So it's about 1/5 of a pound, 0.21 pounds. And then in part B, they keep saying, well, how many ounces will they lose? So we know it's that many pounds. So now if we just multiply by a fraction that includes pounds and ounces, top and bottom, then we can have an answer that has ounces. So how many ounces are in a pound? Sixteen ounces in a pound. So if you made a fraction out of these two, what should go on the top, ounces or pounds? Ounces, because that's your answer. See, if you put ounces up here, and you put pounds on the bottom, then the pounds cancel when you multiply. So 1 pound, 16 ounces. So you take that number that's in your calculator, multiply it by 16, and you get 3.42 or so. So about 3.42 ounces is what you would lose walking for 2.5 hours. Pretty long walk. It'd be like a 6-mile walk or so, 7-mile walk. So then part C and D, they say if a person walks H hours, how many ounces will they lose? And if they walk for M minutes, how many ounces will they lose? So what that does is it takes this whole idea of what we've done with calories and time, and we look at all of these combinations that we multiplied by. So here we multiplied by calories and hours, by pounds and calories, by ounces and pounds, to get to ounces. So I think what I'm going to do is I'm going to show you up here. We have calories in 1 hour for walking, and we have 1 pound is equal to 3,500 calories, and we have 16 ounces is equal to 1 pound. So if you look at this, calories would cancel, pounds will cancel, And you're left with ounces per hour. So by multiplying by a certain number of hours, then the hours will cancel, the calories cancel, and the pounds will cancel, and you'll get some number of ounces. So they say H hours. Well, this is H hours. That goes away, that goes away, this goes away. It ends up being H times 300 times 16 divided by 3,500. So it's a lot of numbers in here. So it's going to be H times 300 times 16 divided by 3,500 ounces. This is a complicated problem. It's good that you ask it rather than just say, oh yeah, we got that one. Not likely. It's a tough one. But if it's m minutes, then you have all of this here. Let me just change color. If it's m minutes, you would take all of this information here, and you would have to change your hours into minutes. So you can put one more thing in here. Hours is on the top, put it on the bottom so it cancels, and put the 60 up there. When you do that, then you multiply all of this out. Then you could say, well, if I'm going to be walking for a certain number of minutes, like m minutes, then this isn't going to get used. Oh, wait, I have a mistake. This is upside down now, because we wouldn't multiply by a bigger number to make even more ounces. We have to divide by 60. You see how hours is now on the bottom twice? When you multiply that all the way across, you have hours here and you have hours here. That can't be. So all we do is we take the same number here, flip it over. Now the hours will cancel out. And then when you multiply by m minutes, the minutes cancel out. So then you'd have m times 300 times 16 divided by 60 times 3,500. So that is not something I would have you go and reproduce again. But if you can follow that a little bit, it helps to reinforce that when we change units, writing in the units helps you to correct your mistakes. You know, a lot of people say, oh, well, I'm going to change it from this to this. I'm just going to multiply by some number. Well, to change, miles and feet, I'll just multiply by 5,280. But maybe you were supposed to divide. And if you don't know for sure whether you're multiplying or you're dividing it, it's easy to make mistakes. So, anything else on 5.6? I'm sorry, 5.4. Okay, then we're going to go to ratios. What's the difference between a rate and a ratio? Do you recall this from days gone by? So when you write a rate as a fraction, what has to be true? about the units. If you had like miles per hour, yeah, then they gotta be different, don't they? But with ratios, the units are the same. So, you know, like if you're comparing two different animals, that's what they do at the beginning. They talk about dachshunds, Labradors, and Greyhounds. And they look at comparing like their head size, and they write it as a ratio. So if we compared the head size of a dachshund to the head size of a greyhound, we could measure how long a dachshund's head is and measure how long a greyhound's head is, and we could write those numbers as a ratio. So ratios will have the same units. So when ratios are written as fractions, they have the same units. We could write a ratio like this, like 4 to 3. We could write it as words, 4 to 3. Or we could write it as a fraction, 4 over 3. But either way, when we do that, we have all the same units. You falling asleep on me? Good. So what it does is it compares quantities of the same units. So you've got 3 terms that come up in this lesson. Ratios, tax rate, and then the third one is discount rate. So ratios, same units. Tax rate. I think I wrote a definition here. Let me write it down right away. When we get to that point of the lesson, you won't have to mix up your vocabulary. So it's a ratio of the tax amount to the selling price, usually written as a percent. And it's a ratio because it ends up being dollars in the end. It's a ratio of the tax amount to the selling price. And then discount rate is the amount that's discounted compared to the original price. So everything gets compared back to the original amounts. You keep that in mind. Doesn't get compared to the total. So those pictures of the 3 dogs are supposed to be proportional to their actual size. I guess we could bring Mrs. Galinsky's wiener dog in here and my retriever, but her wiener dog doesn't like my dog. Her wiener dog doesn't like anything on it. A mean little dog. The only dog that's ever drawn blood on me is a dachshund when I was a little kid. So, which dog has the greatest head length to front leg length ratio? So, Yeah, so if you take their head length and you measured it, and you take their front legs and measured it, which would have the highest ratio? Which would be the longest head to leg? You say dachshund? Hunt? Yeah, if you look at it, if you put a ruler on it even, if you look at the length of its head, it's several times longer than its front legs, isn't it? From crest of its head to its nose. Whereas with a Labrador, they have long legs, and a Greyhound has even longer legs. So which one would have the least head length to body length? Probably the Greyhound, because yeah, the denominator with the body length would be so long compared to its head. And which dog has the least front leg length to body length? So if you measured the front leg length, and you're looking for the least of that compared to the body length, which one would be the smallest?
Like which one has the smallest front legs?
Well, the smallest front legs compared to its body length. Yeah, the wiener dog does. Yeah. So if you read the top to the bottom, like, you go back to the first one, the dog length that has the greatest head length, or the dog that has the greatest head length compared to the front leg. You can read ratios as the first to the second, just like I wrote up here, 4 to 3. So head length to body length or something of that nature. And then front leg length to body length. That's a little harder. The one that's closest to a ratio of 1. In other words, the front leg length and the body length are as close to one another as possible. Probably not the wiener dog, huh? Because their leg length and their body length are so different. How about a Labrador? Does the leg length and the body length look similar? Or is the Greyhound closer to leg length and body length? You think the retriever? Maybe the Greyhound with the longer legs. So if you put a ruler on them and you measured them up. Hello. So if you put a ruler on them and you measured them up, if you went and you measured how long that lab is, it's about 11 millimeter leg. And like from his shoulders to his butt, it's about 18. So 11 and 18. And then if you look at the Greyhound, it's about 12 and maybe 18 again. So maybe because the Greyhound has slightly longer legs, then it would be closer to a ratio of 1. So over the next few days, make sure you have a ruler. Did I give you rulers at the beginning of the year?
No.
I didn't give you like orange rulers? No, so we don't have rulers? Come up with a ruler if you can in the next few days. I've got paper ones probably.
I have some in my binder.
Yeah, rulers can be good. Not in this lesson, but a little bit later in the chapter, we've got to do a bunch of measuring inside the book. All right, well, let's take a look at the problems and see how they lay this out. So it says it takes Max 1/4 of an hour to ride his bike to school. And it takes Riley 21 minutes to walk to school. So write a ratio comparing Max's time to Riley's time. So if they say Max to Riley, you can think of it that way. But mostly what we're going to be doing is writing things as fractions, because what that does is it allows us to add, subtract, multiply, and divide very, very easily. So how long is Max? How long does it take? What did it say in the problem? Quarter of an hour. And it takes 21 minutes for Riley? But we either have to have everything in hours or everything in minutes. What's gonna be easiest to change? Make it all minutes? So what's a quarter of an hour in minutes? 15. So we say it's 15 minutes to 21 minutes, then you can call that a 15 to 21 ratio. Because we now have it in the same units. That's all we have to do with those. You might go and write it again without the minutes. And then if you can simplify it, sometimes we do that. You divide the top and the bottom by 3. So it's a 5 to 7 ratio. So for every 5 minutes of Max's time, you have 7 minutes of Riley's time. Second one, let's look at ratios and percents as tax rates and discount rates. We did a bunch of this last year, and this book isn't going to go and give you all kinds of different ways to solve these problems. But if you remember other ways than what they show in this book to solve problems, you're welcome to use those, as long as you can account for all of your work shown units. So for the second example, you say they have a TV that sells for $400 and it's on sale for $340. And then the tax on the reduced price is $23.80. So the total cost is $363. And 80 cents. So we need to find the discount rate and the tax rate and how much they save by it being on sale. So the discount rate, what is the discount rate by definition again? What did I give to you as that? You have it in your notes? Should write it down. You have to dig it out of the reading. I take time to do that for you guys. Anybody write it down?
The tax, yeah, I wrote that.
Discount.
Ratio of discount to original price.
Okay. So the amount of discount to the original price. So what was the original price? $400. What's the amount of discount?
$340.
That's what it sells for. So how much did they take off?
60.
Took off 60. So if we change that into a percent, then we have the discount rate. So how do you change a fraction into a percent? Remember? Fraction to percent. First of all, you have to change it to a decimal. And then you multiply it by 100%, and you'll have it changed into percent. So change it to a decimal, top divided by bottom, 60 divided by 400, or 6 divided by 40, and then just multiply that by 100%. Someone want to give me an answer? Don't make me do it in my head. You forgot your calculator, I mean, crunch, 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 forgot your calculator. Top and bottom divide by 10, now it's 6 times 10, what's 6 times 10?
60.
Divided by 4. So it's 60 divided by 4, but I could change that to 30 divided by 2, and I can change that into 15. So you don't need a calculator. Just student steps. 15% discount. Then we have to do what, tax rate? So what did I say the tax rate was by definition?
Ratio of tax amount to selling price.
The ratio of the tax amount to the selling price. So the selling price can be 40. What was the tax amount? 2380. Now you need a calculator. So, calculator, 2380 times 100 divided by 340. So that's going to give you the percent tax that's being charged. Seven? Was it some goofy number like 6.9 something? It came out to exactly 7? Oh, that's nice. No rounding needed. So 7% tax. What's Juneau tax? Is it like 10? What's Haynesboro tax?
6%?
How about that
Is it 6 or is it 5.5? I forget. Like 5.5 or 6. It's different if you're in the town site or out of the town site. It's a 0.5% different. A lot of politics with that one. Okay, then what's the last thing we need? Including sales tax. How much would a customer save by buying the TV on sale? So here, this is what they paid on sale. What if it wasn't on sale? How much would they have to pay total? So it's not on sale.
$423.80.
Would you pay the same amount of tax? No. So you're gonna pay $400 plus the tax. And the tax is gonna be 7% of $400. So how do you write 7% of $400? Yeah, 7 times the 400, but that would give you a percent. We need to change that percent either to a fraction or to a decimal. So either call it 7 over 100 or, yeah, 0.07. So I think that's gonna be $28. So how much do they save? Well, the difference between this and this. So you save more than just that $60. You save $60 and the tax on the $60. So I always take discounts before tax. What time are we out? 10 till?
I thought it was 45, but it might be different.
Yeah, I think it's 45.
Is it 45?
No, 5.
It is 45, yeah. So we got 2.5 minutes to do like 3.5 problems. So here's what I do. You did the homework, you did the homework, and you did the homework from yesterday, so you guys have the night off. You do not, you do not. You got stuff to do. What we'll do is we'll come back tomorrow and we'll do the 3rd example and the 4th example. And you'll have work time in class. So maybe you can get out of here tomorrow without homework if you can buckle down with the assignment. And then we'll go into probability and finish up the rest of the chapter. So we're a little bit behind, but that's okay. We've been following it along pretty good. So tomorrow we'll finish this.